Good afternoon, welcome back. Russell Currey is a Linux and open source hacker and Microsoft PowerPoint 2003 aficionado who works at IBM Oz Labs on the Power platform, focusing on Linux kernel hardening and continuous integration. He'll be presenting to us today on using or abusing GitHub Actions for building and testing kernels. Thank you, Russell.
Thanks a lot, Andrew. It's good to be back at the Kernel MiniConf. I apologize slightly for the eye-searing madness you are currently witnessing on your screens, and I'm not just referring to my face. In this talk, I'm going to talk about GitHub Actions for kernel development and why that might be relevant to you. You might be wondering, why should I care about a proprietary, centralized vendor lock-in-ish platform that we don't even use for kernel development? You might also be wondering why you're looking at word art. I hope to answer one of these questions appropriately by the end of the talk. So let's get into it. Let's go over what GitHub Actions is, and then we can look at why it might be of value to us. GitHub Actions is a continuous integration service provided by GitHub. If you think about how a typical software project works on GitHub, if it uses GitHub for development, people send pull requests, and when they send the pull request, their code will get built and tested, and if there's something wrong with it, it'll flag that on the pull request. There'll be like an inline. If it can narrow down the problem to a specific line of code, it'll be there visually in the code review stuff. For release management and builds and publishing, you can use GitHub Actions if you maintain software packages to build for a variety of different platforms and publish that to Docker Hub or whatever. We don't care about any of that. That's not what we're here for. There's one main reason why I think GitHub Actions is quite valuable to us in the kernel development world, and it can be summarized in 3 magic words, and those 3 magic words are unlimited free compute. Now, I'm not sure about you, but when I see these 3 words, my brain produces the happy chemicals. My brain gets excited when I see this. I start thinking of the many possibilities I could take advantage of with this resource. And so it doesn't really matter, well, it does matter, but it's not a deal breaker that the platform is proprietary and centralized when we can use it for unlimited free compute to make our kernel development better. So that's what I'm going to get into today. So to explain a little bit more about why that is, GitHub makes this service available for free to public repositories. Not strictly open source, because you can have a public repository with a proprietary license and that would still have this, but the idea from GitHub is that this is a give back to the open source community, and then you might use this for your personal project, think it's good, and then convince your employer to pay for it. And so I guess that's the business model. So let's get into what it can do and what it can do for us. So if you think about what it can do and how that might be relevant to the kernel, well, the answer is it kind of do anything. It's just a server. You get given a server on which you can execute whatever you want. Except they don't have nested KVM. So that's somewhat of a limiter. But aside from that, anything you can do within a virtual machine running Linux, you can do. The limitation is that you're running inside a relatively crummy VM that, you're not going to be able to make -J200 and have it complete in a minute. You're going to be constrained by that. But there's still a lot you can get done within those constraints. And that can definitely be of value. So let's get a bit more into it. Let's build a kernel. The bare minimum requisite to get some value out of this service is to have it build kernels for us. So let's figure out what we need to be able to do that. So you need a GitHub repository, so you need a GitHub account, you need a repo. You may need to go into the settings of that repo and manually enable actions if you haven't done so before. You need the source tree. You could, within your action, get the source tree from a different repo, but for simplicity's sake, we'll say it's in the same one. And you need a workflow file. This is the special source that actually tells GitHub what to do. This is a file checked into the repository. It's in .github/workflows. So It needs to be committed to the repository. None of this is configured externally to the repository. It all lives in the repo. So you could check this into Git. Good luck upstreaming that, but depending on your workflow. So what's a workflow file? How do we get one? How do we get this going? The workflow is described in YAML, which is another markup language. They're all the same. They all have different syntax. They're all kind of annoying. You need to define within that file what triggers the workflow. So what are the conditions for it to run? You need to describe what the workflow will run on. So what hardware, essentially, what you are asking GitHub for. And then, the meat and potatoes of what does the action actually do. So quickly looking at triggers, this isn't particularly interesting to us. We're pretty much just going to be using push triggers for the workflows I have in mind, but there's a lot of stuff here, and if you go to the documentation, there's a whole bunch of stuff that's probably largely irrelevant if you don't have a very GitHub-centric, workflow already. You can have stuff trigger whenever you push to any branch, whenever you push to specific branches on pull requests, which we probably won't use. Manual triggers, so that's either going in and clicking a button in the UI or making an API request. And there's also a bunch of filtering you can do based on the actual contents of the commit or the body of work. A common example is that you have actions that are going to run tests, and those tests are only going to run if the subsystem that they're testing has actually changed. So if there's no code changes in the subsystem, you probably don't need to waste time testing it on this given commit. So there's a bunch of fanciness you can do there. Now let's talk about where it's actually going to run. We're going to be talking about GitHub's freely provided hosted runners. Now you can provide your own. You can bring your own and give GitHub an SSH key and then run their software on your machine. Though I think it's only x86 and maybe ARM. But then you're buying into a proprietary ecosystem without using their computers for free. So that's a bit less fun. So we're not going to talk about that. Instead, we're going to talk about the two viable options for us, which is Ubuntu and older Ubuntu. There's also other operating systems that you might want for other projects, but we're looking at two Ubuntus. If you're not a fan of Ubuntu, you can, there's container runtimes. You can do whatever you want to get into a build environment you prefer, but you start with Ubuntu. These are hosted on Microsoft Azure. GitHub is owned by Microsoft. GitHub Actions is derivative from Azure Pipelines, I believe. If you've done Azure stuff, you might recognize this class of instances. But they're not too hot, right? You get a 2-core CPU from a Xeon from somewhere in the last several years, from lower end Xeons from 2021 back to Haswell, which is like 24 nanometer, I think. There's 7 gigs of RAM and 14 gigs of disk space per instance. So that is not what you get total across your repository. That is what you get for one configuration of one job at once. So you can have a lot of these running at the same time. It's not like your entire workload must be constrained to this single VM. And finally, we have the workflow file. We have putting it all together to build a kernel. This is everything you need to build a kernel. Well, there's another slide. These 2 slides are everything you need to be able to build a kernel through the system. So let's go over it. We've got a cosmetic name there. We're calling this workflow kernel build. We're triggering it on push, so this will run whenever any push is made to any branch. We are defining a job called kernel and saying that it runs on Ubuntu latest, which is Ubuntu latest LTS. So that will, go out to their gigantic farm of VMs and find one that's idle and make it run your stuff. The stuff that's going to run gets defined in the steps of that job. So first up, we've got a users, which essentially, instead of defining our own commands to run, we are going to use a predefined action. In this case, it comes from GitHub, but you can get actions from anywhere, essentially. There's a marketplace thing, people in the community sharing their own pre-made actions to save you from doing some stuff yourself. So you can look through and find stuff probably of limited relevance to the kernel, but there's certainly stuff out there that could be useful. So in this case, it's just going to check out our repo on disk. So our tree is going to be at /home/runner/Linux or something. Next, we have a run step that we are describing as install dependencies, where we install the dependencies. There is a decent amount of stuff pre-installed, I believe, to build the kernel. I just had to install libssl-dev and libelf-dev, like it had make and stuff, so you should probably manually specify everything just in case. And then we build the kernel, and we're done. That's all you need. Put that in a GitHub repo, and magic will eventually occur. So it works. That's all you need. Someone else's computer has run make for us, which is pretty good. It took 14 minutes and 27 seconds in this case. Not super fast. I could have done that in 2 minutes on my computer, on my power bill. So still neat, right? You can have this triggering all the time. It's not your computer. You don't have to maintain it. This is all pretty good. But it's not really getting us anywhere interesting. So let's look at scaling this up and having a look at what else we can do to get some more value here. Well, this is where we get some value. The kernel has probably infinite scaling configurations of architectures, endians, 32-bit, 64-bit, def configs, just configs in general, platforms within those architectures, ways of running bare metal, KVM, whatever. Matrix is really, really big, and you can scale that up using GitHub Actions. Whatever your matrix is that you don't have time to manually test or to maintain the infrastructure for, you can just get GitHub to do it for you as much as you can within a virtual machine. So you can run qemu on different architectures. You can use different compilers. You can cross-compile stuff. You can use GCC, Clang, different versions of those. You can scale this up hugely, and some of them will run at the same time. You probably won't get an entire data center to yourself, but some of them will run at the same time based on what GitHub feels like chucking you at the time. So you can scale this up pretty nicely and define that through your matrix. There's some quite complicated stuff you can do in there to make sure that you're getting exactly the stuff you want tested in the way you want it. If a n by m size matrix of stuff doesn't actually help you. In this case, we've just defined one variable that we're going to be switching through, which is just the def config. We're still just dealing with x86 here. We're just going to change def config. So we've got 4 instead of 1. And when we run our make, instead of explicitly referring to the def config, we're going to refer to the variable with some funky variable reference syntax. So instead of building one thing slowly, we've built 4 things slowly, but in not too much more time. So this is where you start creeping in with the value you can get out of GitHub Actions. It's infrastructure you don't manage, you don't pay for, that can do a lot of stuff for you without you telling it to. I'll get into it later, but I run some continuous integration using GitHub Actions, and I'm routinely surprised that it's just been running, posting results, not exploding for months without me checking it. So that's some good time investment, I think. So here you can see that I pushed a commit. It took 17 minutes. That's to complete all the configurations defined, all 4 of the jobs. And you can see from the yellow icon thing, those were spinning. So they were all running at the same time. We weren't resource constrained, waiting for more instances. All 4 of them got given one of those VMs at the same time. So that's scaling. Just briefly mentioning before we get into some of the fancier stuff you can do with this. There's first-class Docker support, so if you have a Docker container that you build stuff in with all the nice things that you like, you can give that to GitHub Actions, and then it won't need to recreate it every time. It knows how to do Docker caching stuff. So there isn't that same kind of first-class support for some other container runtimes, but there is people in the community who have done it before, so there is prior art there. Caching, so ccache exists and is cool and is complicated and hard to get a good hit rate on sometimes. And I'm not an expert in getting the perfect special source to make it work in GitHub Actions, but my builds do run faster most of the time from having it, so I'm going to call that a win. GitHub Actions has a cache feature. Your repository has 5 gigs of storage for you to chuck your cache in there. The way it works is that you give it what you want to chuck in there. So in this case, the ccache directory, and you give it a key to refer to it later. So if you want, your cache to be hot, you can, make it so that the key is this specific config, and then you'll use that specific ccache when you build that specific config again later, saving you some time. So you can go up to 5 gigs. If something in the cache isn't hit in a week, it gets evicted. Or if you are running up to that 5 gigs, it will evict the oldest thing to make room. So that's how it works. It's not perfect, but it's pretty good and not too hard to get going if you can. If you're using Docker, maybe it's hard to get the ccache in and out. Problem matches. So this is essentially a way to teach GitHub Actions what your output means. You're running GCC or Clang. It's spitting out a bunch of stuff. Some of it's exploding. Lots of it is unimportant. Some of it is important. How do you get GitHub to know what those things mean? If you're just using this to run stuff for you, you kind of don't really care. But if you're trying to build something on top of it, whether that's you're using the API or you want that kind of interactive feedback that you would get from submitting a pull request where, you introduce a warning on a specific line, it puts that warning on the line in the code review thing, then you can use this. So truncated a lot here, but essentially you chuck it a regex and tell it what the groups refer to, and then it will put that into the GitHub API and present it. So something you can do. This is an example of that. So we've got a sparse warning here. That's what the text looks like when it's just vomited out onto the console output. And with our regex that knows how to parse it, GitHub turns that into an annotation. So it has the job that was run. It has the matrix configuration. So that's going to be PowerPC 64 little endian with PBC 64 LE def config running in an environment that was Ubuntu 21.04 or built on Ubuntu 21.04. And when you click on that, it takes you to it knows the line of code that generated the sparse warning. So you can build stuff on this. Quickly going to talk about getting stuff in and out of jobs. So much like something like Jenkins, you can archive artifacts, and artifacts are essentially the part of your build that is preserved. So, you might want to build your tree for a bunch of different architectures. Well, you can, archive the VM Linux, and then people can run your kernel. In this example, we're just taking a build log. We're saying that, okay, when we build our kernel, it's going to leave its log in build.log, and then we're going to archive it, but with a reference to the def config we used. So at the end of our thing, when we've run all these jobs, we'll have separate archived artifacts referencing each configuration. Then we can refer to them later. So in this case, we are accessing the artifacts from a previous run. And the specific case I use this for is that I will have the maintainers tree. I'll have the base that I apply patches on top of running these actions as well. And so when I run jobs on incoming patches, I have a base to compare it to. So I can tell, is the sparse warning an introduced regression, or was it already there upstream and we shouldn't mark that against this incoming patch series. So this one it's using a community action, not from GitHub, to download an artifact. We say this is the workflow we care about. We only want to look at successes. So if the build failed, we don't want to use the log from that. We specify the branch and we specify the name to put it at. And this lets us do direct comparisons with whatever we previously want to compare to, which is quite important if you're trying to find newly introduced things. You do need to have some other logic that knows how to diff your output, but this is a way to do inline comparison, so you're only flagging stuff that's newly introduced. After you built your kernel, you can boot it and test it. I'm not going to cover that too much, but it's just the same as doing it in a shell script, right? If you already have a shell script, just tell GitHub Actions to run your shell script. You just run it. You take your thing, you boot the thing, you probably write a script using expect, you check if it worked or not, you reconsider your career options, and you carry on. So anything like that is possible. You can because you can take cross compilers, you can build other architectures, you can run stuff inside that. You can run your self tests inside qemu for the thing you just built. So again, lots of possibilities within a restricted environment. Now I'm going to give an example of putting it all together into something quote unquote real. This is what I worked on a couple months of last year doing. So I'm using GitHub Actions right now to run some continuous integration for Arch PowerPC based on the actions that the PowerPC maintainer Michael Ellerman had written, because we were running our CI using Jenkins, and Jenkins is Jenkins. So we have the standard stuff for a kernel development list. We've got our list that all development happens on. We don't use GitHub or anything. I've got my GitHub repository with actions in it based on MPEs. We've got a Patchwork server, so I'll show Patchwork in a sec, but essentially we use it for an API to get the patch series from, and then as an API to push the final results to, so that no one really has to care that this is running on GitHub. That can be kind of transparent. And then there's Snowpatch, which is a tool I wrote that does all the middlemaning. It's, taking stuff, pushing stuff, gluing all the pieces together is what Snowpatch does. So this is Patchwork. If you haven't seen it, it essentially just gives you the state of a mailing list right now. Only useful for that purpose if the maintainer actually uses it, but if they do use it, then we can see here that it's only showing us patches that are currently for consideration. It's not showing stuff that's been accepted already or superseded. On the right side here, we can see some green is successes, warnings, and failures, and this is a result of the tests running on GitHub. So the GitHub actions are being plumbed through here to produce test results. So the process of doing that goes through Snowpatch. It's a daemon that watches Patchwork for new stuff, applies that stuff to a tree, pushes the tree to GitHub, waits for the actions that get triggered from that push to complete, and then sends the results back to Patchwork. And it does that a lot concurrently. So the actual workflows themselves are doing quite a bit. I didn't write these, sprinkled some stuff in that's of lower quality. So PowerPC, if you know anything about it, has quite a wide matrix itself. 32-bit, 64-bit, big endian, little endian, lots of different platforms. We have 64-bit embedded and 64-bit server, lots of different def configs. Still support for the Wii and GameCube. It's a big matrix. So there's a lot of value here in spreading some of that out. Building and testing these lesser, lower priority or just less lower user base platforms, I guess. It builds stuff, it boots stuff in qemu, uses GC and Clang. We use a tool called Smart Sparse Diff to, intelligently split new stuff in a sparse static analysis output from what upstream was showing, and then register a problem matcher on that diff to add annotations just for newly introduced sparse diffs, so we can use that to report test results. And yeah, those actions were primarily written by Michael Ellerman. I just made them worse. And this is the end result. So if you go to Patchwork and you click on the series, this is the kind of thing you see, right? You see, here's the workflows that got run. A bunch of these are running a bunch of different configurations. So, you can see 8 jobs, 24 jobs from the matrix that ran on this specific series. And in this case, that warning is coming from an annotation on GitHub Actions from that problem matcher. So that's how it kind of all goes full circle. And you can see that it knows the specific config that produced the warning, and that comes from that strategy matrix. So that's how it kind of all comes full circle after a lot of GitHub API wrestling. So some other potential use cases for this, aside from this specific one, I think can certainly be of use to subsystem maintainers, because you have a matrix of stuff that you're not constantly testing. You don't always have the hardware to test it. You can keep some of that more niche stuff rolling. Developer pre-submits is another one. A lot of discussion about that in the last few years in general, but one of the hardest things for especially new developers is getting your build environment going, and then then being asked to consider all these other platforms that you don't have to develop on yourself. It's quite daunting. So if you pre-construct something and can just say to a new developer, hey, clone this repo, or open a pull request against it, and it'll test all this stuff before someone on the mailing list tells you you broke 32-bit again, then that can be quite useful. So it could be a very easy jumping off point to cover a lot of stuff that people probably won't test manually, especially if they're not aware of it. Similarly with other architectures, because you can build all the architectures and at least emulate all the architectures in qemu, at least for a smoke test that doesn't boot. Also quite useful when you don't have access to specific hardware, and if one person does it once, everyone can copy it, and everyone doesn't have to individually figure out the magic qemu incantations to boot some architecture you're not familiar with. And yeah, anything with a big matrix that can scale out, you can set GitHub Actions to work doing. So it's worth considering for that. Again, it's not great investing in a proprietary platform, vendor lock-in, etc. But it really is just kind of run it and go, and someone else's energy bill goes up as a result. So I'm a big fan of that personally. Quickly covering limitations. If you are using this on a moderate volume mailing list to test every single patch, it can keep up just fine and run things in a reasonable amount of time. If you ingest a couple months of that mailing list, all creating new workflow triggers at the same time, GitHub will kind of just silently realize that you're a jerk and give you very little. So if you're flooding it with a ton of stuff, you can get rate limited. If you have like a matrix of 24 things on one job, it's unlikely you'll get 24 VMs at the same time. So it's never going to be super time sensitive. Typically, we'll do all these tests and they'll come back in like half an hour to an hour. So it's not glacial, but it's not instant, as is the nature of infrastructure you don't own or pay for. No guarantee you'll get, you might be like, I need this to finish right now, give me a machine. You have no ability to influence that. Sometimes it'll just die. Your job will just fail, an action will fail, it'll just error. Happens infrequently, but it does happen. And finally, if, for example, you had a GitHub repository with thousands of branches that you were using to track every single series on a mailing list for a couple years, and then you merged into that someone's branch that had actions in it, and you hadn't disabled the email that triggers when I got DDoS basically from GitHub to the point where I couldn't receive more mail for the day because my mail gateway had just given up. It had hit its limit, and it took half an hour to delete 250,000 emails from the fast mail web UI. So unlikely anyone will ever hit this, but I felt like I had to talk about it because it was just baffling. And yeah, that's all I had. So happy to take any questions if we still have any time. And thanks a lot for having me. Especially big thanks to Andrew for organizing the Kernel mini-conf yet again. He does a fantastic job. So thanks, everyone.
Okay, thank you very much, Russell. Unfortunately, we have reached the end of the time slot, so we don't really have time for questions, but you can see Russell will be around the conference, and he's got his Twitter and email there, and I'm sure he will be happy to take further questions.
So feel free to annoy me. Thanks a lot, Andrew.